Welcome to another episode of the MDS podcast, the official podcast of the International Parkinson's and Movement Disorder Society. I'm your host, Hugo Morales, and today we delve into an innovative approach to identifying tics in patients with Tourette syndrome. Traditionally, the assessment of tic frequency and severity in these patients has involved manual rating of video by clinical experts using validated scales such as the Roche tic rating scale. In this episode, we explore a cutting-edge approach, automated video-based tic detection using machine learning algorithms. I have with me Professor Alexander Münchau from the Institute of Systems Motor Science, University of Lübeck, Germany, and corresponding author of the paper, Automated Video-Based Approach for the Diagnosis of Tourette Syndrome, published in July issue of Movement Disorder Clinical Practice. Welcome, Professor Münchau.
Hello, Hugo. Nice to speak to you and nice to see you. It's a pleasure to be here today.
Thank you. I wonder if you can start by you telling us about the idea of designing such a study and why was there a need to use a different approach for tic detection?
First of all, we were interested in the question whether it is possible to reliably detect movements, spontaneous movements in people generally. And this first step was done last year and was published also in the Movement Disorder Journal. And it was shown that using the algorithms that we have tested, it is possible to detect movements. But then it wasn't clear, of course, whether these movements we detected were tics in patients or in healthy controls because we didn't compare that. And this was now the second step to test different algorithms whether they're capable of distinguishing between spontaneous movements in healthy controls and tics, supposedly tics in patients with genital Tourette syndrome. There's still a question whether one can identify a single tic and say this is a tic as compared to spontaneous movement. And so the question was, are there some features that can help us to distinguish the two groups? And is this going to tell us something more about the nature of tics in addition to just distinguishing?
I understand that the assessment of the patients that were enrolled in your study were based on video analysis on facial movements, identifying the characteristics of movements in these patients. And that's something that would added to a machine learning algorithm to learn how to identify tics. But
Mhm.
what were the main findings of this study? Sort of how good was machine learning to say, oh, this is tic, this is a tic that differentiates from healthy controls, and what sort of conclusions from these results can you draw from?
So I see this study in a line of studies that need to be done to come to a point where we are actually able to distinguish a single movement. Hopefully, we cannot do this now. We can only say that the movements in group 1 are different from the movements in another group, in group B or so. And these groups are healthy controls versus Tourette patients. And so one of the questions, of course, are there certain features that allow us to distinguish the groups? And one feature is the excess of movement in Tourette patients. So are there simply more movements in these patients compared to healthy controls? But of course, this is not enough because then you could still say what you're measuring are just movements, but does it have anything to do with tics? We're still not there yet. But there are some features the algorithm told us in addition to just the frequency of movements. And this was the clustering, also the duration and the interval between movements. And we could now, with a certainty around 95% or so, distinguish the two groups on the basis of these clusters. So the occurrence of a series of movements in a given time. So the likelihood of such repetitive movements. Now, this is something that from clinical observation, from clinical experience, one would assume, but it has not to take the clustering as one important feature. There are also other features. And now this, of course, needs to be taken further and then validated on a sort of tick by tick basis. But as I just said, if clustering is an important point, then this already shows that a single tick per se or a single movement cannot lead to a firm conclusion what it is, because you need more than one movement to decide what the movement is. And this is one important message, I think, of the paper.
From what I read in the paper, though, the results are quite robust. that these differentiated features that you mentioned, the number of tick clusters and also the duration of them, so will be
Hmm.
relevant to distinguish between patients and controls.
Yeah.
And seeing this clear use of these machine learning algorithms in identifying this patient and looking into future studies or actually implementing such technology in clinical practice. What is your thought about this? What is the feasibility of implementing machine learning to
Hmm.
help clinicians in the diagnostic process?
So first, if we can confirm these data, if they are reproduced, then this would be, I think, an important step to further develop this device into a tool that allows us to distinguish not only tics versus spontaneous movements in healthy controls, but also tic-like movements in patients with functional movement disorders, for example, or the differential diagnosis of myoclonus. Sometimes is it myoclonus or tic? Usually, this is quite straightforward on a clinical basis, but sometimes it can be more tricky. But the distinction between tics, classical tics in Tourette syndrome, and functional tic-like movements in patients with functional disorders can be very tricky. And of course, people can have both in a given person. And this is not only interesting from an academic point of view, but it's also treatment relevant because you would treat tics in a different way than functional tic-like behavior. And therefore, this becomes more important. And of course, you need larger populations to be certain that you can distinguish this, and this needs to be a multi-group effort. So this is step one, so differential diagnosis. Then you could use these algorithms for automatic analysis of video ratings. It can be a bit
Mhm.
tedious if you do this manually and it takes some time. Then you could use wearables and record tics in more naturalistic settings, so at home or in certain situations. It has also been done in other disorders, Parkinsonism and tremor and so on. And because we know that the context, the social context of tics is very important. So then one could develop this further into some sort of variable solution that might be helpful.
Thank you, Professor Münchau. One of the other things that I found really interesting in the study is that actually this machine learning algorithm providing an output and estimating the probability of the tick. And but despite being really good in doing that, still the accuracy was not perfect, and clinicians needed to sort of corroborate the presence
Mhm. Yeah,
of tick. In those cases there was a low probability of tick,
yeah.
and this is a way that clinicians need to supervise AI or artificial intelligence. Is this something that it will become really important if AI or machine learning algorithms come to the clinic?
For the time being, yes, I would have thought so. I think it is very important to still supervise it for quite a long time, probably. And what we also suggested is some sort of hybrid solution in the sense that you use this as a tool, but then there are gray areas where you can't be, where the algorithm is not certain, particularly in those who have few ticks compared to healthy controls. And then in these groups of patients, then in experts come into play and could then help and decide to which group this particular person belongs. And also, as regards clinical rating, usually it is done by two independent raters, and if they disagree by more than 15% or so, as regards tick frequency, then they have a consensus meeting and try to come to a point. And this could also be something where these algorithms help their tools, additional tools in addition to clinical settings, and of course also for unexperienced colleagues who are not so well trained yet, this might be very helpful also as teaching tools. I think of it in the sense that the algorithm can only be as good as we are as clinicians, as experienced clinicians. And if we can feed the algorithms with the experience of a given number of people who have done this for 20 or 30 years, and all these years of experience can enter this algorithm. And it doesn't make us superfluous in a sense, but it helps that all that we have collected across a lifetime is not lost. If I say bye bye to to the clinical setting and then all my experience is gone, this would be a shame, and also this applies to other people. But if we can collect it, save it, then this might be helpful for others in the future.
You're touching a very interesting point about how clinicians do phenomenological diagnosis and probably how AI or machine learning algorithms can point us to the very specific sort of details or nuanced characteristics that may help us to distinguish between chorea, myoclonus, and tics, or even determining the combination of these phenomenologies, which is complex in clinical practice. But hopefully this type of technology can help us to learn about these conditions better. Now, so this concludes today's episodes, and I would like to thank again Professor Münchau for his insights into the potential applications of AI-based technology in the assessment of patients with Tourette syndrome.
Thanks a lot. Thank you very much.
Yeah, thank you, Professor Münchau.
The views and opinions expressed by the participants in this podcast do not necessarily reflect those of the International Parkinson and Movement Disorder Society or their affiliated journals, Movement Disorders and Movement Disorders Clinical Practice. Any disclosures of the participants can be found within the episode description located on the MDS website.